What's going on, everybody? It's Mr. Gus. I'm in the physics conference room. We've talked about engines. We've talked about PV diagrams. We haven't talked about putting them together in a cycle. So today we are. Here's what I got for you. I've got an engine cycle. The engine cycle is 3 steps. It goes in a process, in a cyclical process, okay? We're going to use the first law of thermodynamics to understand this process. Now, we have a 2-mole gas sample, and it's undergoing these 3 processes, A to B, B to C, and C to A. Okay, we're going to look at this and we're going to do some math with it, some SCP-5 practice. Okay, so let's first start. When I look over here, we're going to start by identifying what each of these values, whether it's internal energy, whether it's heat added or lost, or work done onto or by the gas for each process. Okay, so first thing we're going to do before we do any of this stuff, we know the internal energy of a gas is exactly related to its temperature. How is it related? Well, we got it over here. Internal energy is either equal to PV, or 3/2 PV, or it's 3/2 nRT. This is all internal energy stuff. So let's go ahead and solve for our temperature at each process, or at each step in the process. I've already done it. It's right here. A, if I plug in my values for pressure and for volume at A, for pressure and volume at B, or pressure and volume at C, I've already calculated my temperatures right there. So those are my temperatures. What I notice is that A and B have the same temperature. Since A and B have the same temperature, that means there's no change in internal energy from A to B. We would call that the isothermal process. That's 0 joules. Let's label isotherm. That's what that is, okay? So that process is isothermal. I know that, which means I've already started labeling things. Boom, I've already got 0 joules labeled right there. Now, let's go ahead and try to find other processes or other blanks in this table where 0 is able to be filled in. So if I look at the total process, A to B to C to A, that change in temperature is also 0. If that change in temperature is 0, well, guess what? The total internal energy change is also 0 joules. And the cool thing about this is that if the total internal energy change is 0, well, that means that the work done is equal to the heat added or lost. It's the opposite, right? And the same thing is true here. Boom, boom. If those are equal, then, if that internal energy is 0, but then Q and W are also equal but opposite in value. Okay, so we've got those kind of knocked out right now. We know those things. We can also go ahead and if we wanted to, we could solve for the change in internal energy at B and C and from C to A. All we would do is look at 3/2, 2 moles of gas times my ideal gas constant, 8.31, and the change in temperature. Let's go ahead and do that for one of these. Let's go ahead and plug those in for one of these, and we will see, I'm not going to do it for both, but this will be 2 moles, 8.31, and let's go from, let's do from B to C. So from B to C, 962.7 Kelvin minus 240.71 Kelvin. If I go ahead and do all this, I get the change in internal energy is equal to positive 18,000 joules. Okay? Let's go ahead and pop that in. Positive 18,000 joules. That's the change in internal energy. Okay? So I have that there. And I got that by using my ideal gas law, right? My ideal gas law and my internal energy, boom, that's there from the process of B to C. Let's stick on B to C for a little bit here and see what else we can figure out. What kind of process is that? This is an isobaric process. I know that isobaric processes are a little bit strange in terms of the math, so maybe we'll skip that one for a minute. Let's go ahead and look at the work column now, because I can look at this PV diagram, and from the PV diagram alone, I can find work. We learned earlier that work is equal to negative P delta V, or we said it's the area of the PV diagram. So, is there an area from A to B? Yes, it's under this weird curve shape, but there's clearly area under there. How about from B to C? Is there work done there? You betcha. There's clearly a rectangular shape there. There's area. How about from C to A? Well, there's no real area there. There's no change in volume. That's an isometric process. Because there's no change in volume, I would say from C to A, the work done is 0 joules. And again, if this is 0 joules, well, that means that these two things must be equal to. So once I find those must also be equivalent, okay? Which is unique because as I start thinking through this, let's go ahead and see what I can find now. Without doing any more math, let's see what I can find. A to B is 0. B to C is positive 18,000 joules. C to A, I don't know, but I know total I need 0 joules of energy. Well, folks, if this is positive 18,000 joules, this plus this should be total. If the total needs to be 0, I think this needs to be negative 18,000 joules. Check, done. And guess what? If there's 0 work done in the isometric process of C to A, and the internal energy change is negative 18,000, well, if this is negative, the internal energy decreases by 18,000. Well, I think that probably means heat is lost from the gas sample. So negative 18, 1, 2, 3 joules. Negative 18,000 joules is also lost in the form of heat. That's why the temperature decreases. That's why we see a decrease in internal energy. Look at all the fun we're having right now. Now, the last thing we got to look at some point we have to do some actual math. We really have to do some figuring out what these numbers are. So let's go ahead and go back to the work thing. Let's go back to what I think the easier two of work are. So I've got A to B clearly has work. B to C clearly has work. I don't exactly like A to B shape. I'm not very good with calculus. I can't find that shape exactly, so I'm better at geometry. Let's look at B to C. If I look at B to C, what I can see is that this rectangle right here, this kind of shaded region right there, that is a clear rectangle, and the area under that curve is going to be the work done from B to C. So if we do that area from B to C, we can put it over here. So let's go B to C, and I would say that the distance, right, the area is going to be, let's see, the height is 20 times 10 to the 5th pascals. That's the height. The width is 0.006 meters cubed. That's going to be equal to, I've got it written down right here, let me find it from B to C, negative, it's going to be 12,000 joules. And the question is that area positive or negative? Well, clearly the volume is increasing. So using my equation here, the volume gets bigger. That means the gas is applying an outward force. The gas applies a force. I would call that negative work because the gas is using its energy or losing energy. So we'll call that negative 12,000 joules of work from B to C for the work done. Negative 12, 1, 2, 3 joules. Boom. That is done right there. If that's true and it is done, look, I have the internal energy change is positive 18,000 joules. The work done is negative 12,000 joules. The difference between those two is positive 30,000 joules. Right there. That's it. That's the difference. Okay, so I've already got that figured out as well. Now I need to figure out what the work done for A to B is, and this is gross, okay? What you don't know about this is that I actually have a secret equation I can share with you to find it. It's based on calculus, but here's the equation, okay? For an isothermic process, here's the equation we are going to use. For an isothermic process, the area under that curve is work is equal to negative nRT times the natural log of the final volume over the initial volume, okay? This is the equation I have to use because it takes this weird shape. And it is a natural log function, or it's an inverse function, and to find the area of the inverse function, we have to use natural log. If you understand calculus, you probably understand where that equation comes from, and I'm not going to walk through that right now. But it's an inverse function. Because it's inverse, when we take the area under it, it ends up being a natural log. So if I go ahead and take 2 moles, and I multiply that by my by my ideal gas constant and the isothermal temperature of 240.7 Kelvin, right? This is the isothermic process. This is now from A to B. If I do this here and I do my volumes, right? My initial volume was 0.008. My final volume is 0.002. If I do this in the way I'm supposed to do it, I end up with the work done being equal to positive 5,546 joules. All right? On the flip side, because I know the internal energy change is 0 because there's no change in temperature, that means the heat added must be equal to the opposite of that, negative 5,546 joules. Okay? So far, I've got everything filled out except my totals. I've got 2 totals left. Let's just, folks, add these things up down the columns now. So heat added. I have negative 5,546 joules of heat added. Let's take it away. 30,000 added, negative 18,000. The total there is 6,000, positive 6,454 joules. That's how much heat is added to the system. I know the internal energy doesn't change, which means that how much work is done in this cycle, in this perfect cycle, I get 6,454 joules of work done. All right? Let's go back and outline this process. What's the first thing we did? The first thing we did, we found the temperature at the different points. It's the first thing we did. Then, after finding temperature, we were able to find the internal energy, or changes in internal energy between each of the 3 points, using the ideal gas law over here. So first temperature, then changes in internal energy to fill that column in. The next thing we did is we identified any areas that had 0 work and labeled those 0 in our grid. We also found any areas where things would be equal because something else was 0. The last thing we did is we went ahead and we just found our work. We went and found work. We used this graph or this PV diagram to find the area bound by the curve. Sometimes it's a rectangle, awesome. Sometimes it's an inverse function. And if it's an inverse function, we have to use our weird isothermal inverse work equation, which we did over here. Once we did that, we had enough numbers in our table to go ahead and fill the rest in for the entire cycle. Okay? If you got questions, drop in the comments, send me an email, or ask me in class. Until next time, see ya.